When a high voltage line is disconnected like this, it creates an electric spark reaching nearly 9,000 degrees Celsius. This spark is basically a continuous path of current, which means the circuit isn't completely broken even after disconnection. So here's the question. Why not cut the current first and then open the switch? Well, there's actually a device that does exactly that. It's called a sulfur hexafluoride high voltage circuit breaker, or SF6 breaker. Now you might wonder, where does it get its power from? How does it extinguish the spark? And how does it stop the spark from coming back? First, its power comes from a massive spring. You might think, why all that effort? Why not just use a motor? Because that won't work. A motor is way too slow. When there's a fault in the power grid, time is measured in milliseconds, and motors simply can't react that fast. So the breaker uses two heavy springs, one called the trip spring and the other the closing spring. When a control signal arrives, the system does only one thing. It releases the lock on the trip spring. In an instant, all the energy stored in that spring bursts out, creating a powerful mechanical force. But speed alone isn't enough. Here's where sulfur hexafluoride gas, or SF6, plays its key role. And this is the coolest part. The switch rod connected to the spring acts like a piston. As it snaps backward at high speed, it compresses the sealed SF6 gas chamber from just 2 atmospheres up to more than 10 atmospheres. This process is called adiabatic compression. Compression without losing heat. The moment the contacts separate, an electric spark appears. Right then, the high-pressure SF6 gas rushes out at high speed, blasting directly at the spark. Now it's waiting for a critical moment, the current zero point. Let's quickly understand what that means. The electricity in our power grid is alternating current, or AC. It's not a straight line. It's a wave that rises and falls and crosses zero in between. At that zero point, for a split second, the current's value becomes zero. Within that tiny window, just a few microseconds, SF6 gas performs two key actions. First, supersonic gas flow instantly removes the extreme heat from the electric spark, cooling it down in microseconds. Second, it performs deionization. Because SF6 is a highly electronegative gas, its molecules quickly capture the free electrons left in the spark. But even after the spark is gone, the job isn't over. A sudden voltage surge appears across the circuit gap, trying to break the air again and reignite the spark. This is called transient recovery voltage. Now it's a race. Which is faster? The returning voltage, or the SF6 gas building an insulating wall? If SF6 builds that insulation faster, it turns the gap into a solid wall of resistance. That's when we can finally say, the electric spark has been completely extinguished.